Welcome to this third part of this video presentation about lubricants. In this third part I will talk about some base oil. One thing you need to know about when you speak to a supplier of a lubricant is about the API base stock categories. It's not important from a tribology point of view, but you should be aware of those categories of base oils. So there are 5 categories, and group 1, 2, 3 are almost completely made from crude oil, from the oil we are pumping up from the ground. So it includes the higher group number is, the better base oil it is, I would say, and it has, for example, higher VI in itself. The group 4 are the synthetic polyalpha olefins, while group 5 are all other base oils that don't fall into any other category here. So it can be good to know this sometimes when you speak to a supplier of a lubricant. Another classification system that can be good to know is about the SAE viscosity classification for motor oils. You have probably seen on a motor oil can that there is some kind of a number combination written on it, for example 10W40, and that is the first number is telling you something about the viscosity under winter conditions, that's W for winter, and the other is for the summer conditions. So this is for multigrade oils. So a 10W40 means that it has a certain viscosity at in this case at minus 20 degrees, and the 40 tells you that it has another, at very high temperature, it has a certain interval of viscosity. So nowadays we are trying to make oils with as good low temperature performance as possible, and we may also try to reduce the viscosity of the oil to lower the power consumption or power losses in the engine. So we try to have as low numbers both here and here. Viscosity itself, you may already know what viscosity is, but in lubrication we normally work with the dynamic viscosity. So the dynamic viscosity is simply a kind of proportionality constant. It's connecting shear stress with the shear rate gradient. So if you have a surface here and another moving surface here, and you shear it, you form a flow profile that looks like this, and the slope of this flow profile, velocity profile, is the shear rate gradient. So if you have a quet flow, which is normally what you have in a thin film like this, you can simply compute the S as the speed of the surface divided by the thickness of the film. And so this is something you have to measure to get this relationship between the stress and the shear rate gradient. And the proportionality constant is simply the dynamic viscosity. Lubricant manufacturers, they are sometimes using the kinematic viscosity also, because they use viscosity measurement technique that makes and gives an influence of the density of the lubricant. So the kinematic viscosity is simply the dynamic viscosity divided by the density. In this case it's measured in square meters per second, but normally we are using centistokes. So 1 centistoke is 1 square millimeter per second. The dynamic viscosity is, as you know, measured in Pascal seconds, but you can also find centipoise, where 1 centipoise is 1 millipascal second. So it's typically a lubricant is is below 1 Pascal second, so it's of that reason it could be useful to use a number that is between 1 and 1000 maybe. As you have been maybe seen in other videos here about elastohydrodynamic lubrication, the viscosity is, for an oil at least, it's very sensitive to pressure. So if you increase the pressure, the viscosity will increase rapidly. So if you increase it to gigapascal, which you have in EHL contact, you can see here that the viscosity may increase several orders of magnitude. The viscosity can be, at least at low pressures, it's an exponential expression, describes the increase of viscosity relatively well, at least up to say 100 megapascals or so. And then this number alpha is a constant telling you how steep this curve is. The steeper it is, the faster it grows, the viscosity grows. And you can see here that different types of mineral oils, they have maybe this number alpha is even as high as 4 multiplied by 10 to the power minus 8, while other types of mineral oils, you normally have a lower number, polyalpha-olefins even lower, esters, synthetic esters even lower. And look here then, water. Water has a number that is maybe 4 or 5 times smaller than for the oils. But that's even, maybe it doesn't sound that much difference, but if you put it in an exponential function like this one, it has a huge effect on viscosity. And so you can see that the viscosity of water doesn't increase very much when you increase the pressure to, even if you increase it to gigapascal levels. So, and that's the reason why water is so poor lubricant in an EHL contact. Well, the viscosity itself, the eta naught, is of course also very low. So that's also a reason to why it's not very good. And of course, you should remember here that if you have a viscosity like this, it's more like a solid than a fluid. So it reaches a solid state inside the contact. Viscosity-temperature relationships, there are a number of different equations. Here I've only been using a simple, not very exact formula. You can't use the same beta here at every temperature, but on smaller parts of the curve you can use this expression, and you can determine the beta number. You need the beta, for example, if you do some calculations of film thickness and you want to correct it for for inlet shear heating, then you need the beta number. And you see here that the mineral oils have typically higher beta than synthetic ester, and that means that the synthetic ester has are less influenced by temperature. The viscosity is less influenced by temperature than the naphthenic mineral oil, for example. Typically, again, as I said, kinematic viscosity is used in industry, in the lubricant industry, and they may send you a diagram that looks something like this. And it's a little bit strange diagram. It's a double log in this direction, and it's a log in that direction. And by doing that, you actually get almost a straight line, and that's the reason why they are using these strange diagrams. Now you get more or less a straight line like this, and these are standardized diagrams, and there is another classification of lubricants here called the viscosity grade classification, and that tells you that VG46 lubricant, for example, it has a viscosity at 40 degrees of 46 centistokes. So here you see that we are not using SI numbers really, but we are using centi-Stokes in this classification. Makes sense because centi-Stokes gives you a more easy used number than using the square meters per second. There are a number of other important properties of a lubricant or a base oil, like density, compressibility, heat capacity, thermal conductivity, and high shear viscosity. This is how it behaves when you shear it dramatically, which you do in a lubricated contact many times. Flash point is of course important just to avoid that it starts to burn, and pour point is in the other end of the scale. This is the end of where you can use it at low temperature. It starts to form a wax instead. A few words about lubricating greases too. A grease is some kind of semi-solid lubricant. It behaves a little bit like a solid, but it contains a lot of fluid. So it contains the base oil, as we discussed before. It contains additives normally, and it contains then the thickener that creates this solid behavior. And it can be that thickener can be made in different ways, of lithium, calcium, polyurea, for example. And it's typically we say that the grease behaves like water in a sponge. So the thickener is the sponge and the base oil is the water. So you actually fill this structure with base oil, and when it comes into the lubricate contact, the oil is squeezed out or leaked out or to form a film then. So grease is a very complex lubricant, and the knowledge about the understanding of grease lubrication is still poor. There are a few experts in the world on this topic, and I would say that we still need more knowledge about how it works. So as I said before, the thickener forms a kind of network. This is from a thesis from Luleå University of Technology, supervised by Pete Lucht, who is an expert on grease at SKF. And when you put this in a bearing, for example, we believe that the base oil bleeds out from this solid structure, and this bleed oil is coming into the raceway contact between the raceway and the rolling elements, and then it lubricates. And part of this of the thickener may also come into contact, but normally it's the base oil that should bleed out from the solid structure. So this grease, it forms some kind of semi-solid viscoelastic lubricant, and understanding this in a bearing is, as I said, tricky. There are some advantages of grease lubrication, of course. First of all, since it's semi-solid, it stays in place. So if you fill a rolling element bearing with grease, it stays there for a longer time than putting a fluid there, which will flow out pretty soon. And since you have a grease there and you have some solid stuff in the bearing, you also keep contaminants and particles out from the bearing. And as I said, then the process of replenishing the raceway contact is tricky, and it's problematic also, because when you rotate the bearing a couple of revolutions, you will soon squeeze out the grease from the contact. So you rely on the bleeding of the base oil from the grease, which is here and there on the cage and outside the raceway contact. So it must be replenished all the time, but it isn't replenished fast enough to create a full film lubrication. So the EHL equations that I have been showing in other videos, they are not really true for this starved problem. We normally call the the type of lubrication here as starved lubrication because it's not fully flooded lubrication. And normally when you apply this grease, you apply it for the whole service life of the bearing. Even if some bearings, of course, some bearing applications, you put new grease there or continuously. That was a very short story about grease, and then we move to even more solid lubricants. So we talk about solid lubricants themselves. Typical solid lubricants are graphite, molybdenum disulfide, boron nitride, PTFE, and different soft metals. They have in common that they are built up like this. They have some kind of lamellar structure, so you have a pretty strong layer here, but they are connected with weak bonds in between the lamels here, and then you share in those weak layers. So of that reason you get a relatively low shear resistance and a relatively low friction when you lubricate with a solid lubricant, but you never get as low as with a fluid lubricant, of course. Graphite is cost efficient, and it's used very often, but it requires some water vapor to function in a good way, so it's not suitable in places where you have vacuum or in space applications, for example. And it can be used at higher temperatures than the other typical solid lubricant, the molybdenum disulfide. That doesn't need the water vapor, so that is more suitable for space applications. If you have a boron nitride, that's a very strong material, so this one is used for very high temperatures. Well, most solid lubricants are very good for high temperatures or extreme environments. So you don't use solid lubricants in the case where you can use a fluid lubricant or a grease. These solid lubricants are only used when you have so extreme conditions that nothing else works. So boron nitride is then for even higher temperatures. A fourth category is the PTFE. It's not for extreme environments, but I put it here still because it's normally used as a solid lubricant, or it behaves. It's a polymer. It's a solid. You can make the whole surface by this material, but it behaves a little bit like the solid lubricants. And finally, the soft metals like lead, silver, gold. Lead is also possible to share in this way. So it's soft enough. It's a metal, so it carries the load in a good way, but it's easy to share. So it behaves a little bit like a lubricant then. But of course the friction will be high, and you continuously move around the lead and the silver if you have that in the contact. So, but in some applications it can be useful. So that was a very short story about lubricants, and I hope this gave you some interest to learn more about lubricants. Thank you very much.